This is all for Gabe. It's for you, Gabe. Yeah, shout out to Gabe. Yeah. Although they might only be watching the 161 stuff. I don't know. This might be advanced. I don't know. They might. Yeah, you're right. I really hope Gabe is like, that's me. Yeah. Anyways. Last time we ended with talking about the language, right? The language is where we define, like, okay, we're evolving trees. And, I mean, in a similar way, where, just a little better airflow, it's stuffy in here. In a similar way where we define, like, well, with the permutation representation, what are the allowable values, right? We restrict it to a permutation of the numbers 0 through n minus 1, right? It's kind of like the same idea. We are saying, well, what are the available things that can be in the tree? That's what the language is, okay? So it's not even like a new thing for GP. It's the same idea, but we're talking about operators and operands because that's like what's in the structure that's being evolved. And the language that you pick is going to depend on what you're doing, okay? If, like, what was that example I used where I'm like, I used something where I was like, maybe it doesn't really make a lot of sense to do to the, like the sign of something or other, right? Like the sign of the bare nuclei. Okay, that probably doesn't really make sense to include. Maybe it does, I don't know, maybe you can make an argument. But you're going to like discriminate what operators and operands you're going to want in your language based on what you're doing. You're not going to just like create a very large language because as you add more things to the language, you are increasing the size of the search space. So, you know, you want to be careful. You want it to be as restrictive as possible while still being capable of exploring the search space to its full potential to find what you're looking for. So it's always that game of, well, you know. And again, when we're applying these to real problems, we're kind of left going like, I actually don't know what that set is. Like, I don't know what the language should be. You're right. And so you do need to kind of like figure it out. By the way, it's not uncommon for you to have like a basic language, then you evolve like your GP stuff, and then you might notice like a reoccurring pattern in your, like what was evolved. Let's say for whatever reason, it always added like, it always included like x times x or something, right? Like let's say for whatever reason, your whole population was full and then you were getting good results and like all of the good candidate solutions included like x times x. So that might make you go, you know what, I should add maybe like a squared. I should add like a squared thing to my language, right? So it's an iterative process of like seeing what's happening and then learning from it and then basically making it easier for the search to get what it wants. Okay? All right, yeah, so yeah. Depending on what we're doing, you pick your language accordingly. Now, typed versus untyped. I talked about this a bit. I kind of always joke that it's a bit of like a poor name because untyped is still typed, it's just single typed, where typed has just many types. So the mathematical expression above is nice and straightforward in the sense that, here, let's do that. And I'm recording, right? Yeah. It's nice and straightforward in the sense that at any point in this tree, we have a number. I have a literal number here. I have a variable that will be a number. I do subtraction on it. That's a number. Add, it's a number. Everything in here is a number or will result in a number, okay, by applying the operator. So there's no issue there. But like we saw in some of the examples up here, if we have mixing and matching, we're going to have to set our language accordingly where we'll have like comparison operators and Boolean operators. But we have to be careful because like, well, this needs a number and a number, but it returns a Boolean, right? And so what if this expected a number and you were giving a Boolean? Ugh. That's hairy, right? That's kind of tough to manage. Like the if we look at the breast cancer example, there are multiple different types in like some of the suggested functions that we were coming up with. There were Booleans and numbers, right? So we have multiple types. You need to restart. Don't tell me. So some operators act on numbers and produce numbers. Some act on numbers but produce Booleans. Some act on Booleans and produce Booleans. And the operators may, like the literals or like constants or like the variables, the operands, may either be a Boolean or a number. So we need to make sure we can have all of that in like the space, right? So we need to make sure our language is set accordingly. When using a language with only one type, it's called untyped. Bad name, but it is what it is. When using languages that have more than one type, it's called typed. Again, bad name, it is what it is. So because of this, we have whenever you're dealing with typed GP, you have that added complexity of making sure that the S expressions that you are generating are admissible, that they are coherent and are like parsable, right? That they have meaning. You're not trying to like add true to 17, right? Like that doesn't really make sense. Yeah, so if shape equals 4 plus 7, yeah, sure that might work computationally because shape equals 4 is like maybe it's true or false and that kind of can act as a number, but yeah. What's up?
So how would something like the plus sign being like either addition or concatenation, like?
You would have to be careful in how you set things up. And that's going to be programming language dependent, right? So like if you're dealing with a language like C++, where you can override whatever operators you want, yeah, you have a problem where like, well, what does plus mean? Well, it's going to depend on the types, right? So you could very well include plus if you are using strings as well and intend for it to mean string concatenation. But this would all be fleshed out in where you set your language. And every like if you make a GP system all on your own, you'd have to kind of like figure that out. But most GP systems have a mechanism for being like, here's this operator and it acts on Booleans and Booleans. And you can be like, here's plus and it acts on number and number. But here's another one where it's plus and it acts on this and this, for example. Yeah, like a lot of times too, if you define an operator, like if you're doing typed and you have an operator that is like if then else, okay? And a lot of times, like in deep, which we're going to use in this class, like if then else. Well, what are the types of the things? Well, okay, the first thing is going to be a Boolean. And then what's it going to return? Well, it could be a Boolean or a number. It could be a number or a Boolean, you know. So maybe we have to have like a number, num. Then we have to like kind of like redefine it where, okay, num, bool, bool, num, bool, bool, right? Like depending on what it is, although this could become a bit of a problem if its return type can be one or the other. Because like anything above it, it's going to expect one or the other. So that might not work depending on how your system is set up. You might need to be like, well, no, it either is going to be a number or Booleans. It can't be one or the other. Like it's either going to return one or the other to make it like type safe. Yeah, with untyped GP, this isn't a problem because everything is the same type, right? You don't need to be worried about them being inadmissible. The only way they're inadmissible is if like you've generated the tree wrong, where if like you somehow had like an operand down here, or pardon me, an operator down here that had no operands, and then like, wow, that's just not right. But that's not really a language issue. That would have been like how you generated the S expression in the first place, or maybe how like variation operators were applied. Any questions up until now? So genetic programming algorithm setup is really, like I was saying, it's very similar to a regular GA. You've got initialization, evaluation, selection, genetic operators, and termination. It's the same. Crossover and mutation are set for the trees, and that's basically it. And then this is where we really left off last time, right? Bloat, right? So that was good review, bloat. So we have a bit of an interesting phenomenon that happens with genetic programming. So first and foremost, think about if you had a tree of like depth 3, okay? And let's say every node, it's like a binary tree of depth 3, right? Okay, so you've got, not too many nodes. But if you had a tree of like depth 7, it's going to be a lot bigger, a lot more nodes. It's going to take a lot more time to evaluate, too. Okay? So you don't want your trees to be too big. But then again, how big should you let your trees get, right? Is your tree big enough to actually come up with a sufficient solution to the problem, right? Like, if you restrict its size too much, can it be a sufficiently complex function to actually do what you need it to do, So there's a bit of like a question there, and there's also a very interesting phenomenon that over time, as you run your genetic programming instance, the population of trees, the S expressions that you're evolving, get bigger and bigger and bigger over time. However, they get bigger without improvements in fitness. So they just grow bigger, which is weird. And no one really knows why. We've got all these ideas that probably explain why it's happening, but we can't prove it. So okay, so what's gonna happen, right? So when genetic programming, the average number of nodes in a tree starts to increase quickly. And this commonly happens with no actual meaningful improvement in fitness. That's a problem, especially as they get bigger and they get harder to evaluate. And also imagine you've got these big trees. Yeah, I'll come back to this. Well, I will come back to it, but to explain why. But when you have these big trees, the variation operators also become less effective. So they grow, and then they also they become harder to evaluate, and it's harder to change them with our variation operators. So this is problematic. So, okay, they take up more space, they take longer to evaluate, they tend to overfit and generalize poorly, they're difficult to interpret, and the variation operators become less effective. Okay, so there are 3 explanations for this phenomenon: replication, accuracy, theory. 1, parents are selected for having good fitness, right? So think, whenever we're filling up the next generation, we always pick them for having relatively good fitness. Children with a fitness similar to their parents will also be relatively good, right? If the parents were good, and they had a fitness of let's say, about X, and the children of those parents were generated, and their fitness is about the same, around X. And if X was good, that means they're also relatively good, right? Makes sense? Larger trees are less impacted by variation operators. They are. Think about it. If I have a tree that's this big, 4 and 7, I don't know, right? And I go and change one of these things, well, I'm really messing up the totality of what this is. But if you've got this arbitrarily large tree, first of all, as I go down, I have more nodes, right? And if I pick this one, and I do crossover at this point, suddenly this has a much smaller impact. Thus, these larger trees are less likely to be harmed. Because in general, when you do these variation operators, they get worse. At any one point in time, the population gets better, but for the individuals, they tend to get worse. So it ends up actually being better for the trees to be bigger, to be more robust against negative change. That's the problem. You have this implicit selection pressure towards big trees because you can't break them. Mutation doesn't really break them. So they're more robust against negative changes, which is interesting, right? It's pretty neat, right? Does that explanation make sense, right? If 9 times out of 10 I change them, they get worse. but it's better for them to be better. So if I make them bigger such that 9 times out of 10, it doesn't get worse, that's better. So there's like a selection pressure towards bigger trees, which is bad. Removal bias theory. So unless subtrees, okay, useless subtrees with no meaningful function may exist within the tree, like this. Like here's a situation, right? Imagine this is some catastrophically large subtree and it's or true, okay? This is an extreme example, but it gets the point across. With larger trees, there's a higher chance of having useless subtrees, okay? And applying genetic operators to these useless subtrees has no impact. I can change anything in this subtree up to this whole subtree itself, and it's going to have no impact at all, right? Any questions about that one? So another point to be made here, though, that I should be careful to emphasize is when I say useless information, what has been observed in genetic programming is maybe there's something in here that's lying dormant. Maybe there's something in here that was valuable to the individuals, and it got crossed over and it kind of disappeared from the population in terms of it being expressed in the phenotype, right? The phenotype, the genotype of this tree is the tree. The phenotype of this particular tree is true. It always evaluates to true, right? So something in here might be valuable. Maybe it was really important and it just happened to get tossed into here such that it is never expressed. You get like vestigial S expressions, effectively. But if they're put in here, they can be preserved. And then maybe they come back later because we cross over it back into something useful. So when I say useless, I should be careful because it's not necessarily useless. It could actually be value. And it's kind of an interesting phenomenon that effective subtrees, like that x squared, which was really important, maybe it gets thrown into this subtree and it's not expressed anymore. And then like 5,000 generations later, it comes back, right? It's kind of the idea, which is pretty interesting. So yeah, when I say useless, when I was saying useless up here, really what I mean was it wasn't expressed in the phenotype. Yeah. All right, and then there's the nature of program space. There just is more bigger programs than smaller programs that mean the same thing, right? There's only one S expression that means, there's only one S expression that is minimally small that means 4, right? What is it? 4. It's a node containing 4. How many of like height 1 can mean 4? Well, there's more. There's like 1 plus 3, 2 plus 2, 3 plus 1, 4 plus 0, 5 minus 1. There's a lot more trees already at size, to height 1. And then even more, and even more, and even more. So the point is, we're like more likely to find one of like, maybe more likely isn't the right word, but the point is, evolution is just happening. And like we will see examples of this very shortly. But yeah, there's more trees that are bigger, right? So the odds of you having the minimal one, small. The odds of you, like, as you go down, there's more and more and more and more and more, right? So yeah, just think about it. You're more likely to have bigger trees just because there's so many more of them. Yeah? Now, how do you address this? Like everything, there's no right answer. You could set depth limits, which are pretty easy to do in deep, which is nice. Depth limits both in terms of when you generate the trees and when you perform genetic operators. You may not allow like trees to get deeper than like height 5 or something. Now we can make an argument that, well, maybe that's not a good idea because you're biasing the search. You're absolutely right. But at the end of the day, GP is relatively slow. And if you can do things to speed it up, you kind of do things to speed it up. And if you really determine later that you need a bigger depth, then, you know, have at it. But try to keep it small. And okay, not only a tree, set node, like number of node limits as well. You can have special genetic operator rules as well. And here's like a very interesting simple solution is you could have the number of nodes in your tree as part of the fitness measure. So like you can maybe scale your fitness such that if you have 2 expressions that are effectively equal, but one uses fewer nodes, pick that one, right? So you could add selection pressure to encourage smaller trees. And that'll work pretty well as well, which is pretty cool. Any questions about bloat? Bloat's a funny one. All right. Now, we are going to be using deep. Did anyone look at this yet? It's fine if you didn't, it's fine. Deep is distributed evolutionary algorithms in Python. The distributedness of it's kind of, I don't know, smoke and mirrors a little bit, but whatever. It's a nice, it's wildly popular. It's great evolutionary computation system. Okay, you could do basic GAs with it. You could do PSO in it. You could do whatever you want with it. Now, those algorithms are relatively simple. We don't use a system to implement them for our needs, right? But for genetic programming, because I'm nice to you, I'll let you use deep. I would very much encourage you to use deep for your GP system. I suppose technically on assignment 2, which I don't have a due date set yet, but for assignment 2, I should do that soon, eh? I guess you don't have to use deep. You could use whatever GP system you want. You could just go find one and use it, but deep's probably the simplest one. More straightforward to get up and going. When going through it, like part of your assignment 2 is to figure out how to use deep. And if you're like, well, how do I do that? I'm going to say, read the documentation. And then you're going to say, but I did and I don't get it. And I'm going to go, then read it again, because it explains how to use it. There are tutorials. Look, advanced tutorials, GP. Here's how to do GP. Just follow the tutorial and you're good to go, right? Don't tell me you can't figure it out. Then I'm just going to question your literacy. So yeah, deep. It's great. There's a massive API. Don't go memorize this. That would be psychotic. Don't do it. But it exists. Again, read the documentation. Cool. Okay. Genetic programming is like a category. Like everything in evolutionary computation exists in this like hierarchy. Right? There's evolutionary computation, evolutionary algorithms, and genetic algorithms, and GP is really a genetic algorithm. And then there's symbolic regression, which is a specialized form of GP. Symbolic regression is very interesting. What's nice about symbolic regression is it's a form of GP that is untyped, typically, or one type. You're just dealing with numbers. And you're basically doing regression analysis. When I say regression, raise your hand if you have heard the phrase regression or regression analysis before. Raise your hand if you know what it means. Yeah, okay, that's fine. I'll kind of explain it. So this topic, we're going to show how to do regression analysis, symbolic regression, to kind of like understand phenomenon, okay? We're going to use deep. So all of the examples here I'm going to show you is going to be using deep, the thing that you're going to use. So in addition to having the deep tutorial, you can follow along what I'm doing here, and you're going to get a sense of how to use it. And much of the heavy lifting required to implement a genetic programming algorithm is managed by deep, which is really nice. All you have to do is read the documentation. So what is regression analysis? So very simply, there's more to it than this. If you want to get a better answer, ask a statistician. But all I can tell you is we want to find, like let's say I plot this and I go, it really looks like maybe the values on the x and y axis are related in some way. So let's say we have this value x and we have some function of x. And when x is negative 40, we get an f of x around, I don't know, negative 180-ish? I don't know, right? And when this gets bigger, this one gets bigger. In fact, it grows like a line, right? Now, go back to grade 9, where you learned like how to draw straight lines, right? Y equals mx plus b, right? You remember that, right? So I would have said, okay, find the y equals mx plus b for this. And maybe you could figure it out, get something pretty close, but I want to get the best one. Okay, I want to find the best one. And it turns out there's some relatively simple mathematics to find the best one. Like you were guaranteed to find it. We're not going to cover that here. That's not the point. So here's some linear function. When I say linear, I mean that there is clearly a linear relationship here. I can draw a straight line. Okay? So yeah, so given the above observation, the goal is to draw a line of best fit, which should look something like y equals mx plus b, right? Yeah, if you really care, go read the math. It's pretty simple. I learned it years ago from like a Khan Academy video, and I was like, it's that easy? Cool. But fortunately, I don't need to teach you the math. Fortunately, we can load up. We're good computer scientists, and we go, someone's probably implemented that before. So we load up something like scikit-learn, and then we can do regression analysis like that, okay? So there we go. Look at that. So this is the line of best fit. And it's actually kind of interesting. I guess at the scale of what this is, it's hard to see. But you'll kind of notice like the points are kind of like a little bit around. That was by design because real data is relatively noisy. It's just at the scale it is, you can't really see the noise, like the resolution just isn't there. But you can kind of see once we have that line there. So not everything is exactly on this line. What it wants to do is find the line that minimizes the error, the distance from each point to that line, okay? Ideally, we want it to be 0, but it's never going to happen, right? So we're going to get some error, like residuals, they'll call it, right? But in general, that's what we want. Yeah, so the linear regression model for the above observation is y. Now, you'll notice I use this little y hat. And the reason I say y hat here is that's like the syntax you use in the mathematics to mean it's not y. Y is what we observed, the phenomenon that we observed. Y hat is like our estimation of it, okay? It's our like, well, here's what we think it is, right? We concede it's not going to be perfect, but it's pretty close, right? And you look at this, and it's the line of best fit is 0.9998885x plus 0.99 blah, 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 blah. Okay, great. I generated this data a long time ago. I am going to assume it was 1x plus 1, and I added some random noise, and it just so happened that the random noise made the line of best fit actually be off a little bit, right? If I got this though, with like, if I did this with real, and I got this with real data, I'd be jumping to the moon. That's like, wow, that's amazing. That's insane how good that is. But anyways. I also noticed that the scale of these things are way different. F of x, negative 200, and then here, well, I guess it's some other linear function of data. I don't know. It just happened to look the same. Great. Doesn't matter. The point is, I'm looking for that line, and there's some mathematics we can do to find the line that minimizes the distance. This particular, okay, yeah, y hat denotes that it's not y, but it's only like a predictor, a prediction of y, right? So if you gave me an x, I can't tell you what you would really see, but I could tell you that I'm pretty damn sure you're going to get whatever this calculates to, right? About 2. Okay, so if you give me 1, it's going to be about 2, right? Is it really going to be 2? I don't know, but it's going to be close. Okay. This particular model has an R squared of 0.9998, blah, blah, blah. This is a measure of goodness. The closer to 1, the better. That's like what we use. R squared is like a typical thing that you would look at when doing regression analysis to be like, how good was it? All right, the closer it is to 1, the better. If you get something like that, you probably did something wrong because it's too good to be true. Now, the problem with linear regression, however, is it only works if you want to draw a straight line. And unfortunately, in the world, you know, we as humans love when things are simple. We love when we can draw straight lines, when relationships are straightforward, right? In fact, we love it so much that we often make crazy assumptions about things to ignore any nonlinearity just so we can make it fit our linear models, because we like linear models. They're easy to do, they're easy to understand. But unfortunately, the real world's rather complex. You have nonlinear dynamic chaotic systems that's impossible to model and understand. You don't know what the hell's going on. So linear regression is limited in that you can't like find this. Now, you and I, we look at this and we go like, well, that's like parabolic or something, right? Like I don't know what it really is, but I can get a sense of what it is. Now, this is just for illustration purposes. This could look like anything, right? It could look like some crazy function. I don't know, but this is what it looks like. So, yeah, the trouble arises when we observe nonlinear relationship. It's still possible to find high quality models, but it requires several assumptions and a lot of guesswork. So there's a couple of like tricks you can do, by the way, with linear regression, where you say like, okay, this looks like it's like x squared or something, right? It looks like there's like an x squared in there. So you could do linear regression on nonlinear basis functions, which is a fancy way of saying like, and there's a couple ways you can do that, but basically you can like say like, what if your data wasn't the x values, but what if you like just squared all the x values and then tried the linear regression and see like, can I draw a straight line there? If I can, then just square everything, you know? So like you can kind of like cheese it, for lack of a better term, to make linear regression work with nonlinear things. But it does require some assumptions and some guesswork, and there's nothing wrong with that. That's good strategy. In fact, I want to be clear. If you can get away with doing linear regression with what you want to do it. Don't do nonlinear regression. As soon as you show up to a room full of a bunch of mathematicians or scientists and you said, well, I generated these nonlinear, they're immediately like, okay, sure you did, right? Like, good luck, I believe you, right? And you can be like, look, it worked. And they're like, did it though, right? Because as soon as you add crazy nonlinearity, you're screwed. All right, so if I naively go, okay, what's the line of best fit? There it is. This is the best straight line I can draw with this data such that it minimizes the distance from every point to this line. Does that look good? Of course not. That's terrible. Okay? Do we agree? Now, do we have any questions about what I'm explaining up until this point? It's critical that you understand it, and remember, if it's a little unclear to you, ask now, because chances are half the people in the room have the same question. So ask now about like what the problem is and what we're trying to achieve. Okay. So, yeah, here's the line of best fit. Negative 3.07x plus 916 and a half. I don't know, right? Like, okay, but yeah, clearly it wouldn't work. It has an R squared of 0.01. Ugh, that's pretty bad. It's getting close to 0 and you don't want 0, right? And this also, by the way, might be a really good example of why it's often really helpful to visualize your data. Because if you got it and you're like, oh, I guess just my linear model was bad. And you're like, well, how bad is it? And then you're like, oh, it's just, there's no way, right? You're attempting to do something that there's no way it would work. All right, so this is where something like symbolic regression can come in. So an alternative strategy, symbolic regression. There are other forms of other ways and mechanisms and tools that we can use to do nonlinear regression. Symbolic regression is just one of them, and it's one that I like because I like genetic programming. I think it's fun. So what's nice about symbolic regression is it ultimately requires you to make fewer assumptions about the data in order to work with nonlinear data. And symbolic regression is actually capable of finding like the underlying nonlinear relationships. So here's an example of that same data, but I use symbolic regression to fit it. The points are the data, the observations, and the function is the line. Okay, if you plot at every point along like a continuous function, it's the line, okay? So here, it is 1.1 x squared minus 4.44-ish, right? Now, when doing nonlinear regression, you're often not going to use like r squared as a measure of like closeness. What you're going to want to do is something like mean absolute error or mean squared error or like a percent error or something. You're going to use like a different error metric. One that you could easily do for linear regression as well. But r squared is like pretty standard for regular regression analysis. Where symbolic regression, you're using another little one, okay? Long story short, with something like mean absolute error or mean squared error, the closer to 0, the better. You want the error to be 0. Here, I have a mean squared error of 0.1620 whatever, okay? So that's pretty good. Cool. And like, what do I say? By the way, here's a perfect example of like bloat. This isn't catastrophic bloat, but it's a perfect example of bloat. This is the model. This is my y hat. It's got an x squared in it. Great. This is not what GP gave me in the end, though. It would be foolish of me to expect something as clean, as simple as this that GP would give you. Instead, GP will often give you something like this. Okay? Adding the result of doing a division over multiplying x by x over 9, and then you're adding to that the multiplication of x to x, and then you minus 4.4, right? You're going to get something that looks like this. And by the way, we could draw this out for fun. Let's draw it out for fun. So the root is add. And to that, we've got another add, and over here. So we've add. Okay, open, 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 close, close, close. And I guess add, I guess it's just a negative 4.44. I'm going to be lazy, right? And then here, we're adding the result of we're adding the results of the protected divide with multiply x, and then here we're doing protected divide is a special divide where you say like, okay, what happens if you try to divide by 0? Because that would break it. You just say like, I don't know, give it like infinity or something, whatever. Protected divide, and to that we're going to do the multiplication of x and x with 9.95. That's the tree, right? Yeah, I see you're like, yeah, you're right, right? But if you simplify it, it turns into that. So here's an example of like, there's just more bigger programs that mean something nice and tight and simple. You see? It's just going to happen. Simplifying is non-trivial. Some people will say, like, can we bake it into evolution to simplify the trees every once in a while? Well, good luck. Let me know if you figure out how to do that effectively. But also, like, you know, maybe it's important that it's shaped like this because I could do crossover here. Or if I simplified it, I can't do that genetic like you kind of lose that. So, maybe it's good, maybe it's bad, I don't know. Okay. So any questions now? Well, would you agree? This is better. We like this. This is wonderful. Oh, yeah, and I made a comment about mean squared error versus mean absolute error. Here's why mean absolute error is probably a better measure for, like here I'm talking about mean squared error. Typically though, I would say something like mean absolute error or like a percent error or something would be better to give to another human when talking about how good it is. Mean absolute error is nice, it's easy for us to understand, okay? However, through evolution, we like to use mean squared error as a measure of fitness. Can anyone tell me why that might be? It's not a crazy complex problem, but it's tricky to kind of understand. Okay, pretend this is like absolute value, right? So, let's say I'm at like 1. 1, right? If I'm off with mean absolute error, if my error is 1 and I do mean squared error, like my error is 1, okay? Whether I'm here or there or whatever, right? Now if I'm here and I'm at a 2, okay, I'm like, well, that's twice as bad, right? Now, let's think about, I don't really have the alternative. If we have something like this, error of 1 is 1, an error of 2 translates to an error of 4. This effectively punishes bigger mistakes way more. The further we go this way, the way worse we get that way, right? So where here, an improvement from here to here is a unit 1, an improvement from here to here is a unit 1. Where here, an improvement from 2 is a way bigger improvement. It's better to be closer in general. Does that make sense? This helps it get close to where we want it faster. It helps us get close here, right? It's going to rush towards there. Do you see what I mean? So we punish bigger mistakes way more, meaning candidate solutions that address those bigger mistakes, we like a lot more. It helps get the solution closer. But then, when it comes to like talking about results, when you see a value like this, it's kind of harder to wrap your head around. So I probably should be like reporting mean absolute error here, because it's easier to talk about, but it doesn't really matter for right now. Any questions about that idea? You can do whatever you want here. You can make it you can make your fitness measure whatever you want to encourage whatever you want. Mean squared error is pretty typical, pretty simple, straightforward, but yeah. Cool? Like to really hit that point, going from 2 to 1 has an increase of 1, and going from 1 to 0 has an increase of 1. So which is better? Here, going from 1 to 0 is an increase of 1. Going from 2 to 1 is a decrease of 3. See what I mean? So you get like more bang for your buck, basically. Okay, so deep. Due to the complexity, we're not going to like implement GP from scratch. You're not going to do that these days. Instead, we use a system like deep. Many systems exist. Deep is a nice simple one in Python. It's great. It's made by Canadians. So it's fantastic. And it's a package for implementing evolutionary computation in general. You can go to like pip install deep. But even better news, if you cloned the repo and ran like the setup, you have Deep. It would have installed Deep for you. Just activate your virtual environment and you're all set. I will warn you though, that some of like the plotting stuff in Deep doesn't work too well. So just if you're like, how come I can't visualize the tree? Yeah, it is what it is. Some people get it figured out. You can ask me every other year. I remember how to do it. It's a nightmare. Okay, Deep is not only for GP. It's for like everything. Although any genetic program could be used. I really should say GP system could be used. Deep will be used here. The GitHub page is actually here. You go to the Deep GitHub repo. I've contributed to it. And it's encouraged to, contribute to the repository if you can. It's strongly recommended to have a look at Deep's documentation like I talked about. Like the advanced tutorials, some guided tutorials in getting set up, and symbolic regression. It gives a good description of GP in general. So we're using Deep. And then the data. Typically, when doing symbolic regression, you want like your data in like a matrix or in tabular form, okay? Looks something like this. X1, X2, Y. As far as Deep's concerned, well, I guess you can make it work however you want, but often you'll have like the independent variables, and the last one is the dependent variable, the Y. This is what this is what I got when I observed this and this. So the function of like X1 and X2, I want to give me whatever this says. That's the idea here. Columns are like the features, and rows are the observations. Yeah. And we'll stop here because there really is no time to keep going. Any last questions? Do expect to see a deadline for assignment 2 to get posted soon. So, yeah. Awesome. All right. Well, see you all later.